Hello everyone and welcome to this video. Today we are discussing the chapter on wave mechanics. Now previously when we studied the chapter on oscillations, we were studying the oscillations of a single object alone. That means there we were taking a look at a single object or a single particle alone, that is in isolation. However, then the next question to ask is what would happen if a collection of oscillating objects or particles were studied together as a system? And this collection or this system of oscillating particles gives rise to the concept of waves. And therefore now you must understand that a wave is a system of particles oscillating together. It's not something you can find by looking at a single object or a single particle. Now to set up waves in material mediums. So for example, material medium is a medium like air or a liquid or a solid, basically any medium that has actual particles of matter inside it. And to set up waves in a material medium, we see that the elastic forces are the ones that are binding the constituents together. That is binding these particles together so that the motion of one affects the motion of the other. And in order to set up a wave in a material medium, we need that the motion of one should affect the motion of the other. Only then can they result in a pattern of oscillation, as you can see, which we call as the wave. So the next question that we must definitely ask is what exactly is a wave? To understand this, let's take an example. When a pebble is dropped in still water, the surface gets disturbed. This disturbance then moves rapidly outward from the point where we drop the pebble, that is, from the point where the surface is disturbed, and this moves out in the form of circles, as you can see. And if I place a small object, such as a paper boat, on the point or the center of the disturbance, then I see that this object, that is the paper boat, moves up and down, but does not move away from the center of the disturbance. And this brings us to a very important observation about waves. It shows us that the water mass is not flowing outward with the circles, but rather only a moving disturbance has been created. The same propagation of such a disturbance lies under the principle when we are actually talking to somebody. These disturbances which are created by our voices travel through air without any flow of the medium itself. And such a disturbance that moves through a medium without an actual flow of the matter itself as a whole is known as a wave. Which means that wave is nothing but a disturbance which is flowing through the medium without actually moving the particles of the medium. And this is a wave. Now waves transport energy, and the pattern of this disturbance has information that propagates from one point to another. It is through this information that we are actually able to listen to the voices on our cell phones, as these signals are communicated in the form of electromagnetic waves. And this is an example of how waves carry information from one point to another. Now different types of waves are found in nature. These could be mechanical waves, electromagnetic waves as we just discussed, or they could be matter waves. As far as the discussion in this chapter goes, we are discussing only mechanical waves. So what is a mechanical wave? Mechanical waves are associated with the harmonic oscillation of matter, and they depend upon the elastic properties of the medium for propagation. We saw earlier in the video that in a material medium, elastic forces help us set up a wave in the medium. And these elastic forces are required for propagation of wave through that medium, and therefore mechanical waves depend on these elastic forces. Now mechanical waves cannot travel through vacuum. This is obvious because they depend on elastic forces. These elastic forces propagate the wave from one particle to another. Whereas in a vacuum, there are no particles through which the wave can propagate. And the way of propagation of a mechanical wave will not exist, and therefore mechanical waves cannot be set up in a vacuum. Mechanical waves are of two types. The first one is the longitudinal waves. As the name suggests itself, the word longitudinal comes from the word length. And hence you can see that the particles which are oscillating in a longitudinal wave are traveling along the length of the wave. Similarly, we have another type of wave which is known as the transverse wave. From the name itself, you can tell that the particles are oscillating in a different direction than the direction in which the waves are propagating. And therefore, these two types of waves are the two types of mechanical waves that we'll take a look at a little more closely. So first, let's take a look at what we mean by transverse waves. By definition, if the constituents of the medium oscillate perpendicular to the direction of wave propagation, then we call the wave as a transverse wave. To understand what a transverse wave looks like, let's do a simple activity. Consider a slinky held firmly between two ends. If one end of the slinky is repeatedly jerked in an up-down motion, the resulting disturbance on the spring is then a sinusoidal wave, as can be seen. The elements of the string oscillate about their equilibrium mean position as the pulse or the wave passes through them. These oscillations are normal to the direction of wave motion along the string, and thus this is an example of transverse wave. Now there are two ways to look at a wave. In the first way, we try to study the wave as a whole. To do this, we fix an instant of time and take a snapshot of the wave to study the shape of the wave as a whole at that instant. Thus, here we are considering the wave as a system and taking a look at its properties as a system. However, we can also study each individual particle or object inside the system at one time. And therefore, the second way involves fixing a location, that is choosing a point or a particle on the wave and studying this one element of the medium and observing its oscillation in time. Thus, in this way, we are taking a look at each individual element instead of studying the system as a whole. The second type of mechanical wave is a longitudinal wave. By definition, a longitudinal wave is one in which the constituents of the medium oscillate along the direction of wave propagation. We can understand what is meant by a longitudinal wave by continuing the activity that we saw in the transverse wave example. We hold one end of the slinky in our hands and now repeatedly jerk it from left to right to imitate a push-pull motion. The resulting disturbance then is seen to propagate through the spring from one end to the other. Thus, in this case, the oscillation of each particle and the direction of propagation of the wave are the same. This justifies the name of such a wave, that is longitudinal wave, as the word longitudinal implies that the particle oscillates along the length of propagation of the wave. The most famous example of a longitudinal wave is a sound wave. In order to study the propagation of sound as a longitudinal wave, we will take a look at how sound travels through air. To do this, we use a long pipe filled with air and having a piston at one end. When the piston is suddenly pushed forward and pulled back, it generates a pulse of condensations, that is regions of higher density, and rarefactions, that is regions of lower density in the medium, which is air. Thus you can see that the propagation of sound through air is made up of a higher density region and a lower density region. In the propagation of sound, the restoring force causes a change in the density of the medium. However, the compression or rarefaction do not stay at one place. If in a region, compression exists, which means that the molecules in that region are packed closely together, these molecules will tend to move out to the adjacent region such that the density of the adjacent region increases and a compression is moved to the next region. Thus, the compression in that first region is converted into a rarefaction. However, if in a region a rarefaction exists, then the surrounding air will rush in, making the rarefaction move to the adjoining region. So we can see that the compression or rarefactions do not stay at a single place but move from one region to another, making the propagation of a disturbance possible in air. This shows us that sound is a longitudinal wave. Now all the waves that we have considered so far, whether they were longitudinal or transverse, are known as progressive or traveling waves. This is because they are actually traveling from one part of the medium to another. Now let's quickly summarize the important differences between transverse or longitudinal waves. The first point is pretty obvious. We saw that in transverse waves, the particle motion is perpendicular to the direction of propagation of the wave. However, in a longitudinal wave, the particle motion lies along the direction of the propagation of the wave itself. The second point is not so obvious. In a transverse wave, each element undergoes a shearing strain, whereas in a longitudinal wave, each element undergoes a compressive strain. And this actually tells us which medium can a transverse wave actually be set up in. You see, liquids do not have enough restoring force to resist deformation, and hence we know that they don't have a shear modulus, as we saw in the chapter Elasticity. And therefore this means that transverse waves cannot be set up in liquids. They can only be propagated in those media which can sustain shearing stress, such as solids and the surface of liquids, but not inside any liquids. And thus you'll never find a transverse wave inside the bulk of any liquid. In the longitudinal wave case, on the other hand, we know that we can only set up longitudinal waves in those media which can sustain a compressive or a longitudinal strain. And we know that fluids, which means liquids and gases, as well as solids, can all sustain a compressive strain. And therefore longitudinal waves, on the other hand, can be propagated or set up in all types of elastic media, as the elastic properties are extremely important for setting up these mechanical waves. But longitudinal waves can be set up in solids, liquids and gases, and transverse waves can only be set up in solids and the surface of liquids. Now, we already said that whenever we want to study a wave, there are two ways to look at it. One is you either study the wave as a whole, and the other is that you study each and individual element of the wave. And therefore, there are two speeds associated with wave motion. The first one is associated with each particle, and the second one is the speed of the entire wave as a whole. The first one is called as the particle velocity, denoted by v with a subscript p. P stands for particle, and the second one is the velocity of the wave, denoted simply as v. Let's take a look at what each of these mean. The particle velocity, by definition, is the velocity of the vibrating particle of the medium when the wave is propagating, which means that we must take a closer look at each and every single particle, see what is the velocity of this particle that we are looking at, and that velocity is known as the particle velocity. The formula for the particle velocity is given as Vp is equal to omega root a square minus x square. Here, a is nothing but the amplitude of the wave, omega is the angular velocity of SHM, and x is the distance of the particle from the mean position. I want to take this time to point out that you see how omega appears in the formula for velocity. And this should not surprise you. We have literally defined that a wave is a system of oscillating particles. And we saw in the chapter Oscillation that any type of oscillation can be described by a single formula which includes the angular frequency of that oscillation. And since mechanical waves are related to the simple harmonic motion of all of these particles, this omega enters into the speed or velocity of the particle. So omega is the angular velocity of the simple harmonic motion that this particle which you are observing is actually undergoing. X is nothing but the distance of the particle from the mean position at that instant of time when you are actually taking a look at this particle. Similarly, now I can define what is known as the velocity of the wave. This is the velocity with which the whole shape as a whole moves with time, which means that if I take a snapshot of the wave at one point in time and then allow this wave to move from this one point to another and see what is the distance that this wave as a whole has moved, and then ask the question, how fast did this whole shape move from this first point A to the new point B, then what I am actually looking at is the velocity of the wave. And the formula for the velocity of the wave, V, is given as n lambda, where n is the frequency of the medium and lambda is the wavelength, and t is nothing but the time period of oscillation. So V is equal to lambda by t, and this is the velocity of the wave as a whole. Now we have seen that for mechanical waves to be set up in a medium, the medium needs to have certain elastic properties, because we said that restoring force is required for waves to be set up in a medium, and these elastic properties will provide us with that restoring force. And therefore, if I want to write down the speed of a mechanical wave in general, I will see that it varies directly with this restoring force. And therefore, I say that V is directly proportional to the restoring force. Another factor that the speed of a mechanical wave depends upon is its linear mass density. And the speed is inversely proportional to the linear mass density, which means I can say that V is proportional to 1 by linear mass density. Now, using this concept that the speed of a mechanical wave in general depends upon these two factors, that is the restoring force and the linear mass density, I can write down the formula for the speed of a transverse wave or a longitudinal wave. Now, we can set up transverse waves on a stretched spring. For example, if we have a stretched spring fixed between two ends and we move one end repeatedly in up and down motion, we will see that we can set up a transverse wave on this stretched string. We know this is a transverse wave because the direction of propagation and the direction of vibration of the string particles is perpendicular to each other. And therefore, transverse waves can be set up on a stretched string. So what would be the speed of a transverse wave? We will go back to understanding the fact that the speed of a mechanical wave depends on the linear mass density and the restoring force. In case of a wave on a stretched string, the restoring force is provided by the tension T in the string, and therefore I will say that V is directly proportional to T. However, we also saw that the speed also depends on the linear mass density, such that the linear mass density, which is the ratio of mass of the string and its length, is inversely proportional to the speed, and therefore we get that V is proportional to 1 by m. Combining these two equations and applying dimensional analysis tells us that V is actually equal to the root of T by m. And therefore we get the formula of a speed of a transverse wave on a stretched string such that V is equal to root T by m, where T is the tension and m is the linear mass density. And then I can write down the other formula for the speed of a transverse wave as V is equal to root T by pi r square rho, where rho is the ratio of mass and volume. And finally, I will replace the T by pi r square as stress, because by definition, stress is nothing but the restoring forces set up in the system divided by the area. So I get the final formula, which is the one that I want, that V is equal to root stress by rho. And this is the speed of a transverse wave on a stretched spring. Now, using the same idea, I can also write down the equation for the speed of a longitudinal wave, that is, write down what is the speed of sound. Now, we have already seen that sound waves travel in the form of compressions and rarefactions of small volume elements of air. And thus, as discussed before, these elements involve compressional or longitudinal strain. And therefore, the speed of sound will involve the specific modulus of elasticity which is associated with compressional, that is longitudinal strain. And therefore now we know that the speed of a longitudinal wave in an elastic medium depends upon two things. One is the elastic modulus of the medium, and two, the mass density, which now we will denote as rho. And from this I can write the general formula for longitudinal waves as V is equal to root E by rho, where E is the elasticity of the medium and rho is the density of the medium. From this general formula now, I will write down the formula for solids in particular, and I see that the formula is V is equal to root Y by rho, where Y is the Young's modulus of elasticity. Why did we choose the Young's modulus of elasticity? Because longitudinal waves are associated with longitudinal or compressive strain. And this means that the only modulus of elasticity which is associated with the longitudinal stress and strain is Y, which is the Young's modulus of elasticity. In liquids, however, we don't have such a thing as a longitudinal modulus of elasticity. We have the bulk modulus, and therefore the formula for liquids and gases will be V is equal to root B by rho, where B is the bulk modulus of elasticity of liquid or the gaseous medium. Finally, I will say that as solids are more elastic, while gases are the least, this means that E in the numerator of our formula will be greatest for the solids, least for the gases, and liquids lie somewhere in between. And because of this, the velocity of sound is maximum in solids and minimum in gases. But what are the other factors that affect the velocity of sound in air? That is, we are looking at the factors affecting the velocity of sound in any gaseous medium. For an ideal gas, the adiabatic bulk modulus is given by gamma P, where gamma is the specific gas constant and P is the pressure. And therefore, for the speed of sound in a gaseous medium specifically, we come to the formula that V is equal to root gamma P by rho. As you can see, I have replaced the bulk modulus in the numerator with gamma P because this is valid for gaseous mediums for an ideal gas. And therefore now with the formula V is equal to root gamma P by rho, I answer the question, what are the factors that affect the velocity of sound in a gaseous medium? The first one that we will discuss is pressure. Now, although you can see pressure in the formula itself, do not forget that the denominator is density, which means that volume also factors into this formula. Now, at constant temperature, the velocity of sound is said to be independent of the pressure of the gas. Because if temperature is constant, the product of pressure and volume remains a constant. So even if pressure changes, the volume will change accordingly so that the total equation does not change in value. And therefore, actually changing pressure at a constant temperature will produce no change in the value of V. The second one is the effect of temperature. V is directly proportional to the root of T. We also have the effect of density, where it is inversely proportional to the root of density. And finally, the effect of humidity is such that with a rise in humidity, the velocity of sound increases. Just like we wrote down an equation to describe a particle that was oscillating, we must also write down an equation that describes a wave. And this equation is known as the displacement relation for a progressive wave. The word progressive will tell you that we are now talking about waves which are traveling or moving from one part of the medium to another. And to describe such a wave mathematically, we need a function that is both the function of the position and the time. This is because not only is the wave moving with time, each particle of the wave is also moving in position as the wave travels. And therefore, I will write down the equation for a simple harmonic progressive wave which is traveling in the positive x direction, and this equation is given as y is equal to a sine 2 pi in brackets small t by t minus x by lambda, where small t is the instant of time at which you are observing the wave, capital T is the time period, small x is the position at that instant, and lambda is the wavelength of the wave. Now this equation can also be written in another way, that is y is equal to a sine omega t minus kx, and also as y is equal to a sine 2 pi by lambda vt minus x. Now these three equations are absolutely equivalent and we can write them from one form to another. So this was the equation of a progressive wave traveling in the positive x direction. In this case, the displacement of the wave from one point to another is given by the position x, and the distance of each particle from the mean position is given by the symbol y. And therefore, I say that y is the position of each particle and x is the position of the wave itself. But we can also write down the equation for a wave that is traveling in the negative x direction. And in such a case, all we have to do is reverse the sign inside the brackets. And therefore, as you can see, we have written the same three equations but with a plus sign inside the brackets. This is because x will now become minus x and the minuses in the brackets will change to plus. Now note that we can also write down the equation for a simple progressive wave using a cosine function. Now if you remember in oscillations, when we were writing down the equation for oscillation, we were able to use either the sine or the cosine function. Now because a wave is nothing but a system of oscillations, therefore we should also be able to write down the equation of a wave using the cosine function as well. And we can actually do that. And when we write that with the cosine function, we see that the equation is y is equal to a cos omega t plus minus kx. But now the plus sign represents the positive x direction while the negative sign represents the negative x direction. This is opposite to the case that was when we used the sine function. As the wave propagates in the medium, there are alternate regions of maximum and minimum amplitudes, and these regions are known as crests and troughs. And the distance between any two crests and troughs is known as a wavelength. The term in the bracket, that is the term omega t plus minus kx, is known as the phase of the wave. And from this I can see that if x is equal to 0 and t is equal to 0, which means if I am checking at the initial point of the wave, I'll see that if x is 0, t is 0, the initial phase comes out to be 0. And if I'm using the sine formula, then I know that this will mean sine 0 is 0 and y will come out to be 0, which means that the wave has started from the mean position. But this might not always be true. A wave does not have to always start from the mean position. It could start at some different position. And therefore, we come to the idea of a phase difference. That is, how will you know at what point has the wave started? The waves could be similar, but they could just be shifted from each other depending upon what was their initial point of start. And this brings us to the idea of phase difference. To understand what we mean by phase difference, we will compare the wave that we have been studying so far to a circle. That is, I want to tell you how the angles on a circle, the 360-degree angles, can be understood on a wave also. So first what we will do is take a look and observe at the tip of the second hand. Let's say that I'm looking at the tip of the second hand, and we say that we start looking at it when it's at 12 o'clock. So now what I'm going to do is plot the distance of this point, that is the tip of the second hand, distance from the x-axis versus time. So at every instant of time, I will plot the distance of this point from the x-axis versus the time axis. So now I can see that at 12 o'clock, the distance of this yellow dot from the center, that is from the x-axis, is simply the length of the second hand. And as you can see, I have plotted it at t is equal to 0. After 5 seconds, I will plot the new distance from the x-axis at t is equal to 5, and I will do the same for all other different instants of time. And similarly, if I continue to do this, I will see that what I create is nothing but the wave that we have been talking about so far, which means there must be some connection to a circular kind of motion and the sinusoidal function. And this relationship helps us exploit the idea of the phase difference. So now I'm telling you what I mean by a phase difference. If I have a wave like you can see in the picture, and I have some other wave which has not started from the same position. As you can see that the first wave that we are considering, which is shown in white, this wave did not begin from the mean position, it started at the extreme position. Whereas the other wave which I want to compare it with has begun from the mean position. And now I ask you, what is the phase difference between these two waves? So all you have to do is find out how much do they differ in angles. And how will you do that? You simply compare the shape of the second wave with the shape of the first wave, and you will see that the difference is only this initial part of the wave, that is the part which is still in white. And if I compare how much is this difference on the circle, that is on the clock itself, then I know that the angle difference between these 2 points is nothing but 90 degrees, and therefore I say that the phase difference between my 2 waves is 90 degrees. So what have I done? I have simply compared the difference in the 2 waves to the angles on a circle, and when I do that comparison, what I get is the phase difference. And the difference in these 2 waves in simply their distance, that is their positions on the x-axis, is what is known as the path difference, known as delta x. So now that we have understood what it means by phase difference and path difference, let me write down this in a formula. The idea is that in general, the phase of a wave is written as omega t plus minus kx plus phi, where phi is nothing but the initial phase. That's the phase that the wave has at x is equal to 0 and t is equal to 0. Once I have this, I can write down the phase difference between any 2 waves, which is given by 2 pi delta x by lambda, where delta x is the path difference that we just saw and lambda is the wavelength. So this gives me a formula for the phase difference in terms of the path difference. Next, I want to talk about the principle of superposition of waves. Have you ever considered what happens when 2 wave pulses which are traveling in opposite directions cross each other? If we observe closely what happens to these 2 wave pulses, we will see that when the pulses overlap, the resultant displacement is the sum of the displacement due to each pulse. And this resultant displacement, which we call as y, is written as the sum of y1 and y2, where y1 and y2 are the displacements of each of the pulses. And this is known as the principle of superposition of waves. According to this principle, each pulse moves as if the other is simply not present. And this can be seen from the fact that both pulses only affect each other in the area where they overlap. Once the overlap is over, they continue to move as if the overlap did not happen at all, that is, they retain their individual identities. And this is known as the principle of superposition of waves, that is, in the area of overlap, their resulting displacement is nothing but the sum of the displacement due to each pulse. Now, the principle of superposition of waves is very important and fundamental to the idea of interference. The difference is that when we are talking about interference, we are actually talking about 2 waves of the same frequency traveling in the same direction, and when these 2 waves in a medium superpose with each other, their resultant intensity is maximum at some points and minimum at some other points. And from this then I can write down the formulae for the amplitudes and the intensity. The formula for the amplitude of 2 interfering waves, that is the resultant amplitude due to the interference of 2 waves of amplitudes A1 and A2, is given by root A1 square plus A2 square plus 2 A1 A2 cos phi, where phi is the phase difference we just learnt about. Similarly, I can write down the formula for intensity. We have to remember that the intensity of the resultant wave, actually in general the intensity of a wave, is proportional to the square of the amplitude, and therefore I can also write down the formula for intensity using the amplitude equation. That is, I get I is equal to I1 plus I2 plus 2 root I1 I2 cos phi, where phi again is nothing but the phase difference between the waves. A special case of the superposition of waves is the superposition of two identical waves that differ only in their phase and those that are traveling in the same direction. One of the most important cases is when these two waves are in phase. That is, for phi is equal to 0, the waves are in phase, and the resultant wave comes out to have an amplitude which is 2a, that is the largest possible amplitude that the wave can have. This means that the two superimposing waves, when they exactly match each other in shape while traveling across each other, in such a case we have what is known as the constructive interference. Similarly, if these two waves, on the other hand, are completely out of phase, that is, if the phase difference is pi, then the resultant wave turns out to have zero displacement everywhere at all times, and this is known as the destructive interference. So far, all the waves that we have been discussing were progressive or traveling waves. That is, they travel from one part of the medium to another. But sometimes waves do not move, rather they just vibrate in place. So how does one create these waves that are not moving but vibrating in place? To do this, we will see that when two simple harmonic progressive waves of equal frequencies and amplitudes are traveling through a medium in the opposite direction but along the same line, and then when these waves coincide, then the resultant effect is there is a wave which does not travel. And such a wave is known as a stationary wave or a standing wave. And as you can see, that the resultant effect of these two progressive waves, wave 1 and wave 2, is this white wave, which is a stationary or a standing wave. It is not moving. The blue and yellow waves are moving, but the white wave is just vibrating in place, and the white wave is our stationary or the standing wave. If we observe the position of the wave at a particular instant of time, that is, if we take a snapshot, then when we are observing a particular position x, we will see that at this particular position, the resultant displacement y of the stationary wave is nothing but the sum of the displacement y1 of the first wave and the displacement y2 of the second wave. And this is us applying the superposition principle to the stationary wave example. And thus we get the equation of a stationary wave, and it comes out to be y is equal to 2a cos 2 pi x by lambda into sine 2 pi nt. And the reason we've written it in two brackets is because the first bracket actually represents the amplitude of the wave itself. And you will see and wonder, why is this amplitude such a big expression? Why is it not simply a like we had before? This is because the amplitude of the wave itself is varying, and therefore the amplitude has a complicated expression. The second half of the equation tells us about the shape that the wave is taking, and as you can see, the shape is sinusoidal. And this gives me the equation of a stationary wave, and I can also write this down as y is equal to r sine 2 pi nt, where r of course is nothing but the amplitude. So I've written the amplitude as r. That means r is nothing but 2a cos 2 pi x by lambda, and a is nothing but the amplitude of each wave. Lambda is the wavelength of each wave, and this is the equation of a stationary wave. Now, as the wave vibrates in its place, it is observed that there are some points on the stationary wave at which the particles have zero amplitude. That is, these points are not moving and are always at rest. These points which never move are known as nodes. And the location of nodes is given on the wave as x is equal to lambda by 4 or 3 lambda by 4 or 5 lambda by 4 and so on and so forth. That is odd multiples of the quarter wavelength. Similarly, we will also observe some other different types of points on the stationary wave. That is, points on the stationary wave at which the amplitude, that is the particles, oscillate with a maximum amplitude, and these points are known as antinodes. The location of antinodes is then given by x is equal to 0, lambda by 2, lambda, 3 lambda by 2, so on and so forth. That means these are even multiples of the quarter wavelength. Since lambda by 2 is nothing but 2 lambda by 4, lambda is nothing but 4 lambda by 4, 3 lambda by 2 is nothing but 6 lambda by 4, and so on and so forth. So the location of the antinodes is given in such a way, and you will finally see that the nodes and antinodes are equispaced at intervals of lambda by 2. The most significant feature of the concept of standing or stationary waves is that the boundary conditions decide the possible wavelengths or frequencies of vibration of the system. This is quite different from what we saw in the case of a simple harmonic traveling wave. This is because in that case, the wave could have had any frequency. However, in case of a standing wave, depending upon the boundary condition, the wave will be able to vibrate only with a certain set of frequencies. And this set of frequencies is known as the natural frequencies or the normal modes of oscillation. And therefore, it means that what frequencies the wave will vibrate with is decided by the boundary condition. So now let's take a look at the standing or the stationary waves on a string and see how the boundary conditions affect what frequencies it will have. For a string stretched between two fixed points, we can see obviously that the endpoints will act as nodes. This is because by definition, nodes are those points on a wave which will never move. And if you fix these 2 points at the end for a string, then by definition, these 2 points must be node. And this is your boundary condition. Your boundary condition is that the endpoints of a stretched string on which a standing wave must vibrate, these endpoints must definitely be nodes. And then of course you will see that in between then you will have an antinode. And from here I can draw the diagram of vibration of a string for the first case, that is when I have only one loop of vibration. Then I can see that the effective vibrating length, which is also known as the effective length simply, is nothing but lambda by 2, because this is actually half a wave if you carefully look at it. But a string can vibrate in more than one way. I can still have my condition that the nodes are there at the end points if I vibrate the string in 2 exact loops. In such a case, I will have the 2 nodes at the end points, which is definitely what we want. But then I will see that in between, instead of having only one antinode like the first case, now I have 2 antinodes and a node that separates them. So this is also another way in which a string can vibrate between 2 fixed points. In such a case, now I will see that the effective vibrating length is made up of one whole wave, and therefore the length will be lambda, or I can say 2 times lambda by 2. And then we can also move on to another way in which the string can vibrate between 2 fixed ends. I still have nodes at the 2 ends, but now I have 3 loops in between. And now in this case, I will see that the effective vibrating length will be 3 times lambda by 2 as shown in the figure. Now the first way in which the string was vibrating, that is when it made one loop only, is known as the fundamental mode. In such a case, the effective length was half the wavelength of the wave. In the second case, we call it the first overtone, and in the second case, the effective length was twice lambda by 2, that was simply lambda. And in the third case, that is where there were 3 loops of vibration, we call it the second overtone, that is L is equal to 3 lambda by 2, it was 3 times lambda by 2. And therefore, I see that the fundamental mode is when I have one loop, the first overtone is when I have 2 loops, the second overtone is when I have 3 loops. Now, what is the difference between overtone and harmonics? Harmonics include the fundamental frequency, which means the fundamental mode will be the first harmonic, the first overtone will be the second harmonic, and the second overtone will be the third harmonic. So we can write down an equation for the frequency of the stretched string as it vibrates by looking at how many loops the vibration has. We already know that the distance between 2 consecutive nodes is lambda by 2, and in order that the endpoints are maintained as nodes, the length L, as you can see, must be an integral multiple of lambda by 2. In the first case, it was the first multiple of lambda by 2. In the second case, it was the second multiple of lambda by 2. And in the third case, it was the third multiple of lambda by 2. From this, I can write down the general equation which tells me what is the effective vibrating length. It will be n lambda by 2, where n could be 1, 2, or 3. And now I can connect the number of loops of vibration to the fundamental frequency. In general, if the string is vibrating in p loops, then the frequency of vibration in the pth mode is given np is equal to p by 2l root t by m, where p is the number of loops, t is the tension, and m is of course the mass density. And this will be equal to P times the N1, where N1 is the fundamental frequency, that is the frequency of the fundamental mode. Therefore, it means that you can write down the frequency of vibration by knowing the number of loops. And now, as I have said before, this means that the number of loops is equal to the harmonic which you are talking about. The first loop corresponds to the first harmonic, 2 loops corresponds to the second harmonic, and so on and so forth. And therefore, P loops will correspond to the pth harmonic, and the overtone is found by subtracting 1 from this number. And therefore, if I want to write down the formula for the fundamental frequency, I only have to put P is equal to 1 in the same formula, and I get the formula for the fundamental frequency, that is N is equal to 1 by 2L root T by M. That is, I got the fundamental mode frequency simply by putting P is equal to 1. And these are the equations that are relevant for the standing waves on a string. Using the formula for the frequency of vibration, we can write down the following relations, which are known as the laws of vibrating string. The first one is the law of length. It says that if T and M are constant, then N is inversely proportional to L, as you can see from the formula. The second one is the law of mass. It says that if T and L are constant, then N is inversely proportional to the root of M, again as evidenced from the formula itself. The third one is law of tension. It says that if L and M are constant, then N and T are directly proportional, that is, N is proportional to the root of T. And finally, we have the law of density. For a fixed volume, mass is directly proportional to density, and therefore, whatever is the relationship between N and mass, the same will be the relationship between N and density, and therefore we get the law of density as if T, L, and P are constant, then N is inversely proportional to root of rho, where rho is the density. So these are the laws of vibrating string. Now, just like stationary waves can be set up on a stretched string, they can also be set up in an air column. And just like we use the boundary conditions in a stretched string to write down the position of nodes, antinodes, and the frequency of vibration, we can also use the boundary conditions to write these same expressions for an air column. Now, when we want to write down the boundary conditions, we'll be looking at 2 types of air columns. The first one is when we have a pipe which is closed at only one end. The boundary condition for such a pipe is that the end which is closed is considered to be a node, because this end is fixed and can't move, and therefore I must have node, that is N, 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 at the bottom of each of these 3 pipes. And then obviously for the open end, we will have the boundary condition that the open end must be an antinode, and I write AAA at the top of each of these pipes. And then I can identify the nodes and antinodes in between, because I know nodes and antinodes occur in alternate succession. If I take a look at the pipe which is open at both ends, then the boundary conditions will be such that at both ends we will have an antinode. And therefore I will write AAA at the top of each of these pipes and AAA at the bottom of each of these pipes, and fill in the node and antinode picture in between, knowing that nodes and antinodes will be alternately placed. A closed organ pipe is an example of an air column closed at one end. To see this, we can actually hold a pipe inside a beaker of water and then send waves down this pipe by taking a tuning fork, hitting it on a rubber pad, and allowing the wave to travel down the length of the pipe. We will see that the wave is actually reflected because of the water, and therefore this resembles a pipe closed at one end, because the water is actually closing the pipe at one end, and at the top the pipe is open, so this is a pipe with one end closed. In such a case, then I will apply the boundary conditions that we have spoken of before, and then write down the equations for the nodes and the antinodes. And we will see that since the closed end must be a node and the open end must be an antinode, the possible wavelengths will come out to be odd multiples of lambda by 4. Thus, the normal modes of vibration are then given by the expression n is equal to 2k plus 1 v by 4l, and this is nothing but the equation for the frequency of vibration. And since, just like a stretched string, there can be more than one mode of vibration, we can write down the expression for each of these modes. I will see that in the first case, the effective length is lambda by 4. In the second case, the effective length is 3 times lambda by 4. And in the third case, the effective length is 5 times lambda by 4. And you can see that 2 times lambda by 4 and 4 times lambda by 4 are missing. And this has happened because of our boundary conditions. And therefore, I see that only certain frequencies are allowed, which is what we said happens in case of stationary waves. In this case, the expression 2k plus 1 gives us the number of the harmonic and k gives me the number of the overtone, which means that if I want the fundamental mode of vibration, I simply have to put k is equal to 0 and that will give me the formula for the fundamental frequency of vibration. That is n is equal to V by 4L. Similarly, we can also take a look at the open organ pipe. The open organ pipe is an example of an air column open at both ends, and then using the idea of the same boundary conditions as before, we know that the two open ends must act as antinodes, and therefore the possible wavelengths will come out to be multiples of lambda by 2. In the first case, we have 2 parts of lambda by 4, and therefore the effective length is actually lambda by 2. In the second case, we have 4 parts of lambda by 4, and therefore the effective length comes out to be simply lambda. In the third case, we have 6 parts of lambda by 4, and the effective length comes out to be 3 lambda by 2. So you can see the effective length comes out to be multiples of lambda by 2. And thus the normal modes of vibration are then given by n is equal to 2k plus 1 V by 2L, where k is equal to 0, 1, 2, 3, etc. K plus 1 gives me the number of the harmonic and k gives me the number of the overtone. Therefore, the fundamental mode of vibration will simply be given as before as k is equal to 0, and in this case the fundamental mode of vibration is n is equal to V by 2L. Finally, remember that in the systems above, whether we had strings or air columns, these systems can also undergo forced oscillations, and if the external frequency is close to one of the natural frequencies, the systems will show resonance. Another interesting phenomenon is the phenomenon of beats. Consider 2 harmonic waves having close frequencies and the same amplitude. When these 2 waves are superimposed upon each other, there is a periodic variation of the intensity of sound between the maximum and minimum with a frequency equal to the difference in the 2 close frequencies, and this is known as beats, which means that if you are listening to 2 sound waves which are equal in amplitude but very close to each other in frequency, you will hear 2 kinds of sounds. One with the same frequency of the waves, approximately close to that, and second will be a frequency which is equal to the difference of these frequencies, and this second frequency is known as the beat frequency. Now this wave will have an amplitude which will vary in time. Although it will oscillate with the average angular frequency, the amplitude will vary in time, that is, it will not remain constant in time, unlike a pure harmonic wave. The time interval between 2 consecutive maxima or minima is known as the period of beats and is given as the inverse of the difference between the frequencies, that is 1 upon n1 minus n2, where n1 and n2 are the frequencies of the 2 waves which caused the beat phenomenon. The beat frequency is then given simply by n1 minus n2, provided n1 is greater than n2, or n2 minus n1 if n2 is greater than n1. Another interesting phenomenon that can be observed in our daily lives is the Doppler effect. For example, if an ambulance is sounding its siren and is stationary on the road, and you are also stationary with respect to the ambulance, then the frequency or pitch of the sound does not change with time. However, if you are standing at one position, but the ambulance is moving towards you, you will see that the pitch of the sound increases. On the other hand, for a person from whom the ambulance is moving away, the pitch of frequency seems to decrease. This is known as the Doppler effect. The Doppler effect can also be observed in case of light waves. If we know the frequency of light and then observe the frequency of light coming from a star, and we see that the frequency is increasing, then we'll know that the star is actually moving towards us. Historically, this was one of the ways in which we understood that stars were actually moving away from us. Scientists observed that the frequency of light coming from the stars was actually reducing, and this told us that all the stars were red-shifted, which is what we say when the stars are moving away from us, and this is the Doppler effect in case of light. So this means that the frequency that we are observing is actually the apparent frequency. And to write down the formula for this apparent frequency, conventionally the direction from the listener to the source is taken as the positive direction of velocity. We'll denote V as the velocity of sound, VL as the velocity of the listener, Vs as the velocity of the source, N as the real frequency of sound, N dash as the apparent frequency of sound. And now I can write down the apparent frequency in different situations. In the first situation, we only moved the source, that is, the source of sound is moving, but the observer is stationary. And this gives rise to two cases. First one is that the source is approaching a stationary listener, and the second one is that the source is receding away from a stationary listener. This will give rise to two equations for the apparent frequency. Similarly, we can also have the other situation in which the listener is moving, but the source is stationary. This will give rise to two cases, one where the listener is approaching a stationary source, and the other where the listener is receding away from a stationary source. And finally, we could also have the situation in which both the source and the observer are moving. In one case, they could be moving towards each other, that is, they are approaching each other, and the other, they will be receding each other or moving away from each other. So these are the formulae for the apparent frequency that we will observe of the sound. So this completes all the concepts that I want to revise with you under wave mechanics. Thank you for watching. Thank you for watching this video. If you like our channel, please click subscribe. And if you'd like to get your very own Target Publications book, click on the button here on the left. Thank you for watching.